Let's talk about database consistency. Imagine you are writing an app that enables people to choose a seat on an airplane and buy it. So the app would work likely in this way. You would display to a user the map of the aircraft with the seats labeled, and the user would be able to click on an empty seat and buy it. And when the user clicks on an empty seat, the code you would you would run in order to respond to that request would look something like this. Probably a bit more complicated, but this would be the basic idea. So you would receive a request to buy a certain seat ID. So you would read the seat, and then you would check. If the seat is still free, then you mark it as occupied. You say set is free is equal to false. You would mark who the buyer is. You would set it to the email of the current user, for instance, and you would say success is equal to true, so the user succeeded in buying the seat. And otherwise you would set success is equal to false, and then you would update the seat on the database and also return success to the user. So the reason you need to check that the seat is free when processing the request is fairly simple. There could be multiple users looking at that flight, and so a user can look at the screen map of the plane for a long time. So you cannot trust that the seat free or busy status hasn't changed from when the user loaded the map of the aircraft to when the user actually chooses a seat and clicks. Okay, so when the user clicks, at that time you need to check whether the seat is free. Now the issue is this. There could have been another user who in parallel was also looking at the same flight. And this is what the other user is doing. So the other user is doing exactly the same request. The other user, of course, has a different email, right? And so has a different identity. But the code they would run when they click on buying the seat would be the same. Just it would happen likely in two different servers for your web application. So one possible execution is this. Time goes from top to bottom, of course. And what could happen is that the first user reads the status of the seat. Then the second user reads the status of the seat. Then this happens independently in the memory of each one of the two different servers. So both users would say, hey, is the seat free? Yes, it is. Oh, I'm lucky. I mark the seat as bought by the current user who requested it. I set success to true. And this would happen also in the other server, okay? And then you would first write it here for user 1, and then write it here again, okay? So if you wrote the code in this way, what would happen is this, that both users click on the button to buy the seat, okay? To both users you reply that they succeeded, so they believe that they have reserved their favorite seat in the aircraft. But actually user 2 request overrides the one from user 1, so the seat would result bought by the user 2, okay? Because seat.buyer would be the email of user 2, and this write would overwrite this one, okay? So what we are seeing here is a classical consistency problem, okay? Due to the fact that you have many web servers and requests can happen to you at any time, if you are not careful about concurrency, about the possibility that code is executed at the same time, you can have that there are inconsistencies created in the database due to this parallel processing of the requests, okay? Of course, if the order changed, if the timing was slightly off in the other direction, then the user 1 would have succeeded in buying it, even though to both of them you would have sent a confirmation. So what we would like to do is to have some way of essentially ensuring that these read, modify, and write happen in a way that they don't interact with each other in some way, right? We would like to have some notion of processing either the request for user 1 or for user 2 independently from each other. Not in this way. In this way, they are called interleaved. They are like a deck of cards when you mix it, right? Because there is this is interleaved with this that happens next, then there is this, then there is this, and then there are the two rights. So this is an example of interleaving. And what you would like to do is rather isolate and keep logically separate what you do for user 1 and for user 2. So this brings up the general point. How do you isolate the processing of different requests on the database? So to ensure that this kind of read, modify, write interaction doesn't happen, you can have in databases what is called isolation levels between transactions, precisely to keep them separate. There are 4 isolation levels, and I would like to tell you how they work. They are called read uncommitted, repeatable read, read committed, and serializable. So read uncommitted, I think I nickname it as the garbage level. You can read no matter what happens, and any possible disaster can happen. So I think the simple fact is don't use it. In fact, it's not even available in some databases such as Postgres, okay? So the real contest is about the other 3, and we want to know what do they mean. Repeatable read means the following. If this is time, you could have a process, this is your process, that is reading the same piece of data twice. For example, it's doing a query and then it needs to read it again. The same piece of data, okay? So the same, say, row in the database. There could be another process here that at some point it decides to write, okay? Repeatable read means that these 2 readings of the same piece of information will give you the same result. So this is the meaning of repeatable read. It means things do not change from under your feet. So this is a bit informal, but I think it gives you the very good feeling for what a repeatable read is. Repeatable read is not the only one. So what is the meaning of the next one that is important? The next one is read committed. Read committed can be understood as follows. Let this again be the timeline. And imagine that there is a process that wrote some data and then did a commit. Commit means I'm done working, I want all my results to be written. This is a commit. And this is a write. Imagine that you are writing your own process here to work on the data. Okay, and imagine that here there is another process that runs. Okay, so this is time, no? And this is a line is also the data. So there is this process here, let's call it P1 who committed some write. Then there is a process P2 who is thinking what to do and has written something but has not committed anything yet, is not yet done. Okay, P1 is done, P2 is still in doing stuff. Now you read that piece of data. The question is, which data do you read? Do you read the final result of P1 or do you read the intermediate result of P2? P2 will only commit later. Maybe it will do some other stuff and it will commit later. Okay? So, what do you read? The answer is that in read committed, what you read is this one. Okay? You read the last value that has been committed. And the intuitive meaning of read committed, which is, by the way, the standard for Postgres, the intuitive meaning is that I don't want intermediate result. Okay, so your rights do not matter until you decide that you are done writing. Okay, I will not take your intermediate results as good. Okay, so this is a different thing from the previous one, of course. Repeatable read is things do not change under your feet, but you may be reading things that are that have been written in haste, provided you always read the same thing whenever you access a piece of data. Okay, provided the value does not change between two reads. Read committed means do not give me intermediate results. I just want the final result. But read committed may read things that are different if you read twice, because, for example, in read committed you could have this phenomenon that you have two short processes that write some data and then commit it. Let me simply write and commit, and then here you could have again that they write data and they commit it. Okay, and then your longer process can read the same data twice, right? It can read it here and it can read it here, and this read will read the result this right, and this read will read this right. Okay, so read committed does not guarantee that you read twice the same value if you do execute the same read instruction twice. Okay. Then there is a final level of consistency that you can ask for, and that is called serializable. And serializable, among these various levels of consistency, is the only one that, in my opinion, it truly makes sense. The other two are convenient because they are easy to implement and they give rise to efficient database access. But serializable access is what truly makes sense from the point of view of a developer. Serializable access means this, that you can have your own reads and writes, and you can do something very complicated. So this is your process. Okay, this is time, and this is another process that can also read and write and read again and write again and then commit. Okay, so there are two processes running in parallel. And serializable means I don't care how you do it, but to the user, logically, the final result on the database and on these processes should be as if either these went first and these went second, or perhaps vice versa, these went first and these went second. But the things are happening as if they were happening in a serialized way, that is, in series, one after the other. Okay, the database may choose to do things simultaneously as an optimization if you access different pieces of data, but the final result is as if one full unit of processing happened entirely before the other. Okay? In practice, databases implement serializable, these are called transactions. Once you go to serializable, transactions means a series of stuff you need to do in a way that does not depend on other things. So traditionally databases, what they do is this: they if you give them two things to do in parallel, they try to do them in parallel, but they keep track of whether one is disturbing the other. Let me give you a concrete example. Let us return to our database example. Okay, imagine that these two people are buying different seats in different aircraft, or even simply different seats on the same aircraft. Then the database would say, there is buyer 1 and there is buyer 2. Yes, they're reading values and modifying values, but the values they read and modify are not the same, so there is no conflict. So I can let both things happen simultaneously, and to the user it will still look like either one or the other went first. There is no contradiction. Okay? If the database, however, detects that these two people are trying to buy the same seat, so that this read modify write is on the same seat, the first user who will buy will succeed, and the second user, when it tries to buy, will fail. Okay, and it will get an error, and it will get a retry error, and so your web app will do something like, I'm sorry, but something went wrong. Please refresh the page and buy another seat. I'm sure it happened to you while trying to organize your travel. So let me tell you how this choice happens in code. So how can you choose a transaction level? So what you need to do in order to enclose some code like this in a transaction is the following. You need to say db execute SQL start a transaction. So actually, let me put it here so that you see how it is really done. You need to start the transaction at the beginning. Okay? Actually, you need at the very beginning to set your transaction isolation level. So this you need to do when you connect to the database, or at least before you start the transaction. So here, for instance, db execute level set transaction isolation level, and here we would choose for this serializable. Okay, so you would choose serializable transactions for this particular application. Okay, then you would start the transaction. Okay, you would do whatever you need to do. Okay, and here you will need, so theoretically people tell you to write a commit. Okay, but what happens is that you don't need to write a commit in this way. You can use our database abstraction layer to write a commit in this way. Except that, as I mentioned, the commit can fail in case there is interaction from another thread. So whenever you use a serializable isolation level, you cannot do simply commit. You have to do try database commit, in which case you can return success. Okay. Else, and in fact, let me retry is equal to false, so you don't need to retry. Else, what you need to do if the commit fails is that you need to say something like db.rollback, which means I know that my transaction interfered with something else that was trying to be achieved in parallel, and I know that it failed. So please roll back all its effects. It's like an undo operation. Okay, this is what in an editor would be an undo. Since I failed and I, could have left a mess informally, then you say please undo my changes. Okay, and here we would say return dictionary of like retry is equal to true. Okay, and success is equal to false in that case, of course. Okay, so this means that you have to display some message to the user saying, I'm sorry, I failed to buy the seat for you, etc. Okay, so databases have this ability of giving you serializable transactions. So serializable transactions, so to go back to our drawings a little bit, mean the following, that to give you yet another interpretation on them, okay, that if this is time, you can have a lot of users that access your site all at the same time. There can be user 1 request, a user 2 request, then there can be a user 3 request, there can be a user 4 request. It can be a global mess, and these requests do not need to be on the same server. They can be, for example, some of them on the server 1, some of them on the server 2, some of them on the server 3. So what you have is a situation in which there is a lot of stuff going on at the same time. And this is one of the most difficult code to write, code that manages at the same time simultaneous things that can happen in any order. Because the hardest condition in which you can write code is the one in which stuff is changing below your feet. You don't know when it changes and you don't have full control on the situation. So serializable isolation means essentially that the database is giving you this incredibly nice mental model in which so time is still going on, and these user transactions will appear to you logically and from the point of view of their effect as if they happened in some order. You don't know which order. I mean, the order depends on a choice internal to the database, okay? But to you, logically, it's as if they happened one after the other. And so the incredible thing that databases give you is this simplicity of mind, that when you think about processing the request from one user, you can momentarily ignore the existence of all other users if you use a serializable level transaction. Okay? This is an incredible mental simplification. It means, let me pretend that this is the only thing actually happening in parallel in the database, and I can focus my attention on answering that request. If there are multiple requests in parallel to the same server or to different web servers, the database somehow will figure it out and will give me a series of results that is logically equivalent from the point of view of data left in the database and defect to the fact that these units of processing called the transactions happened one after the other. Okay, this is one of the main benefits of using databases in a web server. They give you not only data storage, but they give you this incredibly simple mental model of things happening one at a time, which is really what enables us to write simple code to answer requests. Okay? And so what you should get out of this class is the following. Read and commit, nobody uses it. Repeatable read is the default for MySQL, and read commit is the default for Postgres. Okay, and serializable is what actually isolates requests. Okay, so if I give you this model, you will say, okay, serializable is a good one. Why are the defaults different? Okay, and why do they exist, and why do I ever use them? The answer is this: serializable is the mentally sane concept, but it's a little bit expensive because a database needs to do this analysis of whether there is a transaction that might interfere with what is going on. Okay, and if you have a very high level volume of requests, it is actually expensive to check this non-interference property when you are serving 500 requests simultaneously, as it happens in large commercial databases. Okay, in many cases, because of various other reasons of how the logic of your web application goes, that different threads cannot really interfere with one another. Let me give you various examples. Imagine you are editing your own user profile. Well, other user profiles, your user profile cannot be edited by other users. So you know that there is no interference. Yes, there could be an interference if you are logged in both from a laptop and simultaneously from another laptop that you may have, and then you keep the two laptops open in parallel and you hit save on both laptops at the same time. You could, there is always a way in which you could do that, but you generally assume that users are not competing with themselves, right? So if you are updating a user profile, then you don't need to worry about a serializable transactions. Another case, imagine you are developing an email program, okay? And I can say that that email, now I file it under the, urgent emails. I'm presumably the only person that has access to my own emails, right? Emails are personal. And so when I change the tags of emails or a file under the folders, etc., and the database has to reflect my decision, again, you don't need transactions because you assume that there is only one user doing that. Okay, so you can go for the cheaper route. And many things in the end work like this. Okay, It is only the case of when you have these, you have a read, a modify, and a write. Read, modify, writes among data that is shared by multiple users, those need to be protected by serializable transactions. Okay, if you are just reading, you don't need to do anything special. For example, if you're just reading which seats are available, you don't need to do a transaction. Okay, because you cannot conflict with anything. I mean, the worst can happen is that you are reading all the information. Okay, so in practice, when you develop this web code, you need to think, am I doing a read, modify, write of data that is shared among multiple users? And if so, you have to do a transaction, serializable transaction. If not, you can just trust your database default level of transaction isolation, which is repeatable read for MySQL and read committed for Postgres. You should also remember in MySQL that the repeatable reads you're doing is just the most recent data. It may not be data that is committed. And similarly in Postgres, when you read, you are reading data that has been committed by other processes, but you are not necessarily reading twice the same data if you read it twice. This means that, for example, in Postgres, let me give you a concrete example of where the strange effect can come in. So in Postgres, if you write code such as row is equal to db bird of 3, okay, and then you say if row dot flies, you can say x plus equals 1, okay, you say x is equal to 0 here, okay, and then you repeat this code actually twice. Okay, this is a silly example, but it will do just fine. Okay, so you would imagine that here in MySQL x is either 0 or 2. Okay, because when you read twice you get the same value. But in Postgres x can also be 1. Okay, so that is the difference that can arise. Postgres does not have a repeatable read, but it has a read committed. Okay, so these were two different philosophical choices. And so again, this is a rule of thumb. When you do a processing of a request, you have to consider, am I doing a read, modify, write, such as this one, of shared information? If so, I need to protect it. If not, I can trust the default level of isolation of the database.